All right, we're here looking at linear inequalities. So linear inequalities are quite simply very similar to linear equations. They're inequalities with two variables, usually x and y. And so what happens with that, we're going to graph them exactly as we would a regular line. Slope, y-intercept, and so on. We do have two additional rules. Number one, similar to how when we solved inequalities in one variable and graphed our solutions on number lines, we used a closed or solid circle, dot, for less than or equal to and greater than or equal to. We're going to use a solid line when we graph linear inequalities with less than or equal to and greater than or equal to. Similarly, how we used an open circle or dot for greater than and less than, when we're going to graph a linear inequality using greater than or less than, we're going to use a dotted line. And then the other rule is we have to shade the set of all points, the set of all ordered pairs that are solutions to the inequality. Remember, just like with inequalities in one variable, we have an infinite number of ways to satisfy that inequality. So we need to indicate that somehow. We do that by shading. So let's actually look at an example. So I would like to graph y is greater than x minus 2. So I have a slope, which is 1 over 1, and a y-intercept, which is at 0, negative 2. Again, think about this just as you would for slope-intercept form. What's attached to x is your m, which is 1 here, and your b is the number after with its sign, so negative 2. All right, so plot your y-intercept, 0, negative 2. Use your slope to find another point, up 1 over 1. And then because this one is a greater than, according to my rule, I need to use a dotted line. So I'm going to do that. Now after that, we need to shade. There's two ways to think about that. I like to think about it as above the line, below the line. I'm using a greater than symbol. So I would say in a situation like this, I should shade above this line. Right there. Now, you can prove this mathematically. You can show why you shade that part of the graph. Let's pick a point where I just highlighted. Let's use the origin. Let's see if the origin satisfies this inequality. So y is greater than x minus 2. The origin, of course, is 0, 0. So let's plug in our values. 0 is less than 0 minus 2. And simplify. 0 is greater than negative 2. That is correct. That is valid. And so we know that 0, 0 is a solution. So we shade over, we color over the part of our graph that includes 0, 0. If we had found that the point that we tested was not a solution, we would shade the other side of the line. So with that, you can prove it mathematically, but as I said, you could also just kind of think about greater than or equal to, go above the line. Less than or equal to, go below the line. Let's actually see a less than. So if we look at the next example, we see that we have y less than or equal to 1/2 x plus 1. We're going to start this the same way. Our slope and our y-intercept. Our slope here, our m, is 1/2. Our y-intercept, our b, is 1. So our y-intercept is at 0, 1. Plot your y-intercept, 0, 1. Go up 1 and to the right 2 using your slope, right? Up 1 and to the right 2. And then we're going to use, in this case, a solid line because it's less than or equal to. So now I have to decide about shading. So My way to do this is to say, well, y is less than 1/2 x plus 1. I'm going to shade below the line. So, again, you could test a point for that if you would like. But, again, this works as well. Graph our line. It's solid because it's less than or equal to. Also, because it's less than or equal to, we shade below. All right. I'm going to give you a chance to do something. So why don't you, whether on a piece of paper, a tablet, whatever, go ahead and try to graph y greater than x plus 1. So hit pause and then hit play when you're done, and we'll check our answer. So here's our answer. So our slope here is 1/1. It's 1x. And our y-intercept is also 1 at 0, 1. So I graphed that. I went up 1/1 to the right. Got my second point. I used a dotted line because this was greater than. And then because also it was greater than, I shaded above the line. All right. There's two other kinds of inequalities that we can talk about. What happens if we have only one variable and a horizontal or vertical line? You don't want to go back to your old days of open circle, closed circle, and drawing arrows. That's not quite correct here. What we want to do instead is we want to actually graph these as horizontal and vertical lines. So I know that if I have an x by itself, that's a vertical line. For x and 2, we want to talk about the points on our graph where our x coordinate is 2. That's all of these along this vertical line. Right here. Okay? And it's solid. I'm using less than or equal to. Whoops. That should be moved over to -2. So, now I have to decide how to shade. Okay? So it's less than or equal to. Now, horizontal and vertical inequalities are actually easier to graph than ones with, both slope and y-intercept, because it's really easy to identify the numbers you want. We want the numbers, the x's, which are less than -2. Well, the numbers to the left of it. And in this case, it kind of follows what you have learned in the past, where you have said, well, if I have less than or equal to, I shade to the left. We have one other type of inequality, the vertical inequality, horizontal. So we have y greater than 6. Well, we know that anything that is y by itself with no x, we have a horizontal line. In this case, it's dotted because it's greater than, not greater than or equal to. And again, vertical and horizontal are a little easier to figure out where to shade, because you just have to think about where are y's greater than 6 above it. All right, that's it. Thanks for watching.